Right, so the next speaker is John Pretty. Actually, I had a hard time to practice my speech because I didn't know what to say. As you all know, John Pretty, he's the organizer of this event, and today he's going to talk about dependent types, and we will see how it goes.
Thank you, we certainly will. I didn't sleep last night. I got some advice about 3 months ago from Łukasz that if you're organising a conference, never do a talk as well. So I ignored that. You know when you've been out drinking the night before and you don't really remember what happened, and then the following day you meet up with a friend who was out with you, and they start telling you details of what happened. Well, in my sleep-deprived state, I've got no recollection of what I wrote at about 4 a.m. this morning. So each slide is going to be a surprise to me. And I will be I'll be playing this by ear. Apologies that it's not as finished as I would like, but I'm going to jump in anyway. I'm going to be talking about a use for dependent types using Scala, and I've chosen this picture of a slippery road. Now I wanted to contrast this with I wanted this slippery road to represent sort of dynamic languages and the lack of control they give you, and I could potentially contrast it with, for example, a train line which runs on rails. Except Rails has been stolen by the dynamic community, so I can't use that analogy. So I'm going to be talking about using dependent types, lots of detailed, precise typing information, taking advantage of that to give us safer code, more type-safe code, and overall more reliable software. That is our goal. So does anyone know what this does? I'm not meant to ask questions, am I? This will list the contents of a directory. This is a bash or a shell command, and it consists of several parameters. It's ls. It's got the parameter l, which is long listing, a, which shows everything, h, which I think shows human readable file sizes. It's going to sort the files in time order, and it's going to format that to a width of 120. So we've got several parameters here. Now, it's not a particularly complex problem to parse those parameters and come up with a data structure in our program to represent them, and then usefully use those parameters in determining how we implement our ls command. It's a common thing we have to do, but I think we can still do better than most solutions to this problem. Who here is, can you just show your hands, who has had to write a command line application at some point? So virtually everyone. Now we want to parse those parameters in some typed format like this. So L, A, and H, well they're merely present. They have no additional information, so I'm just representing them as units. Sort, well that's the string time, and width is an integer, 120. So this is what we want. This is kind of what we want to get from those parameters in string format. So let's make a first attempt at doing this. So we've got a CLI object, and we're going to call parse on that with args. Args is an array of strings. It comes straight out of the main method. And we try and get the sort parameter. We call command line.get sort. So this is a reasonable first attempt to get a parameter out of a reasonable API. I haven't shown you the implementation, obviously, but a reasonable API that we might use to get that parameter. But the size was actually an integer, so we can include a type parameter here. Now, what you can't see in this method call is that this is probably resolving a type class based on int, which knows how to parse the string version of that and return an appropriate value as an integer. So we're adding typed information here, and this is an improvement over the previous one. Everyone with me so far? Nobody's with me. You are allowed to sort of say yes. Thank you. Now, size is sometimes written S-I-Z-E with a double dash before it, and sometimes you just use the shorthand -s. So we want to support both of those possibilities. So let's change our API so we include a single character for the short version. Now what this means is that every time we try and get this integer, we're having to mention the type, which is int, the short version, and the long version. This is quite verbose, and if we need the size more than once, we're repeating ourselves. So let's try and improve that. Let's define a parameter called sizeParam. So this is just a value. It's a case class called param. We specify the int here. We specify the s and the size. This will capture the type class that we can use and reuse. And everything else is the same, and we're getting sizeParam this time. Might succeed, might fail. The sizeParam might or might not be there. So I think this API we've come up with is gradually improving. We're repeating ourselves less, and we're getting better type safety in general. Now I've spoken several times about an idea called modes. Who has not heard of modes? Okay, enough that it's worth me talking about them. So modes was an idea I came up with a few years ago now for dealing with different ways of handling errors or failures. And what I've said here is it allows you to use the same API to handle failures differently in different contexts. So same API, what I mean by that is the same method signature. You're calling the same method. It's not like a similar one, a copy of the original one with a different return type. It's literally calling the same method. Handling failures, well these are exceptions or exception-like things. And handling them differently, by that I mean, for example, capturing them in a try, or in a future, or perhaps just returning an option rather than the actual value. And by different contexts, I mean in different scopes. So being able to specify the scope of your code in which a particular mode applies. So here's some examples. We can determine whether we get the raw typed value out, whether we wrap it in try, whether we wrap it in option or future, or it's extensible. So we have multiple possibilities that we can add ourselves. And the way we control it is by either declaring or importing a mode type. We import that into scope, and within that scope, it'll seem like magic. It's not magic. It's not even macros, but it will determine how a method returns a success and a failure typed value. Now the implementation of this might sound a bit contradictory, is simple but advanced. It uses 3 advanced features, but the usages are really simple. And those features are implicits, higher-kinded types, and dependent method types. So each of them is reasonably advanced. And it's been in Rapture for several years now, or maybe 2 at least, and is usable and works. And I'm pretty happy with the seamlessness of it. So it's something that works. Now I'll give you an example. If we import modes.return try, and we try and parse this. Now this is not valid JSON. I haven't closed the array. So this is going to fail. And with this, can you see the cursor there? It's a bit subtle, isn't it? With this import in scope, we will get a try of JSON back. Whereas if we had return option in scope, we will get none back. Still a failure. We're doing exactly the same thing here. This is exactly the same method call. It's just that there's an implicit parameter that gets resolved there, and it's this return option type rather than the return try. You can also have return future. So does this seem magic? Does it seem not magic? Ah, okay, right, it's not magic. It is not magic. I did tell you that before. So dependent method types. What the way these work is they allow you to have a method return a type that is dependent on a parameter to that method call, and typically of the refined type of the parameter. Now what I mean by that is if you have a function, fn, which takes a parameter called mode, or type mode, we can have that method return the inner type of that mode. So what happens in the compiler is when you call fn, it finds an instance. Sorry, it's not implicit yet. You pass it an instance of mode. Now the mode type always has a return type as an inner type. And when the compiler receives this or sees this parameter provided to the fn method, the type of that parameter, well, it is mode, but the compiler knows something more specific than that. It knows it's actually m.type. And m.type means it can actually, if it knows m and m is stable, it can actually resolve what the return type is. Now I haven't provided the actual implementation because implementations are boring. We like types. I'll save value level code for lesser conferences, I think. And so we can return this completely different type on the basis of a different parameter provided. So this is the first step. Next step is type constructors. Who's familiar with type constructors? Okay, about half. So a type constructor allows you to construct a new proper type from an old one. So you can construct, for example, a list of int from an int. You can construct a list of string from a string. List, in both cases, is the type constructor. List is not a proper type itself, because you can't just have an instance of list. It has to be a list of something. It might be list of any, it might be list of nothing. But either way, it is the type constructor. Option is a type constructor. So you're actually very familiar with these already. I think I'll put this away. You're familiar with these already, but maybe you didn't think of them as type constructors before. So these are a bit like functions at the type level. Now we can change our inner type in mode to a higher kind of type, a type constructor, which takes one parameter. This is the syntax we use. So I've added in yellow the change we've made. We've also called it wrap now. And rather than just returning m.return, we can return m.wrap of a specified type, int in this particular case. I chose it arbitrarily, but we are wrapping the proper type in the implementation of this method here. Again, I don't care about the value level. That can be worked out later. So this is combining both dependent method types and higher kinded types, and that all works fine in Scala, more or less. And finally, implicits, which I'm sure everyone is familiar with, but maybe not completely familiar. These let us specify a parameter, not so much explicitly, but by grabbing it from the surrounding scope by its type. So we want to get a mode. So we make this method, this parameter implicit, and when we call fn, it will look in the surrounding scope. It'll find a that doesn't look great, does it? Let's just leave it unselected. It will find hopefully this try mode here, and the return type will be m.wrap. Now m is known to be try mode, assuming we call this in the same scope, and it will wrap int, so we'll get a try of int. So these three things together give us a mode. Now each of the examples I showed you, returning futures, returning options, are examples of this these three features combined. So like I said before, it's advanced, but I've used each feature reasonably minimally in terms of the complexity for that particular feature. So So I'm going to take a minor departure now. I didn't see this coming. To talk about rapture internationalization, or I18N. So this was something I came up with a few months ago for representing strings in different languages. So we frequently find that we have we have some software that needs to output text to a human, and the human may understand English, French, German, or some other language. Now this is pretty familiar stuff. Often applications will have a messages file, one for each language perhaps. But we're going to define all of our messages in the code itself. I like Scala. I like writing code. I don't want to introduce some new format for representing different languages and text. So this is valid Scala code. This uses a string context. I've provided 3 different versions of the same phrase, one in English, one in French, one in German. And we're basically saying, well, it's either English, which is hello, it's French, which is bonjour, or it's German, which is guten Tag. And that's a single value representing all of these strings. So it's a bit like a map. Now, if I include the type in there, the type has resolved to iString of en with fr with de. So this is an intersection. It's the intersection of 3 different types. These exist in the library. There's one for each language that's included, and all ISO languages are in Rapture I18N. So the type of this thing we've just created has encoded the actual values that are there. English, French, and German. Now what that means... Oh, no, let's look at some bullet points. Which will probably just reiterate what I've just said. So we're representing a string in different languages with a single value, which is a map, and different types representing each language. And we are tracking, or we're storing those types in an intersection. That's the width. And that is a type parameter to the map. This is a slightly simpler version. I haven't included German. Removing German simplifies everything. I didn't plan that one. I might regret it in the next break. So this is actually the English, and I've explicitly included the type there. So this is iString of en. So this is what it looks like if you've only got one language. Again, same again with French. And we're calling the pipe method on the first value, providing it the second value, and this is this becomes en with fr. So this combinator, this pipe, is taking the type parameter of iString here, the type parameter of iString there, and it's intersecting them to return this. Now, this might seem a little bit odd. I think maybe the next line says it's a bit odd. No, okay. I'll first show you an example of a simplified version of the iString. So this is the implementation of pipe. We have language 1, and when we combine it with we're using alternation. When we combine it with another iString, we are producing this return type. Again, I'm not bothering with values. This return type, which is the first language with the second language. So that's how those types are composed from the 2 values to produce that return type. Nothing particularly complicated, except you might be wondering what this type means. What does it mean to have an L1 with an L2? I haven't even shown you an instance of L1 or L2, or an instance of en, or an instance of fr. So traditionally, maybe not amongst this audience, but traditionally, if you include a type as a parameter to another type, like list of int, you normally expect there to be instances of int around. Naively, maybe you expect that. But there's no reason why you have to ever have instances of those types. There are ways we can use that type parameter, useful ways we can use that type parameter without ever having an instance of them, which is quite convenient because if you have an en and an fr, what does it mean to have something that is both an en and an fr as a subtype of both of those types? It doesn't really have much meaning. So what we can do with those types, rather than ever have instances of them, rather than ever store values of that type, we can use that en with fr with de type as a constraint on operations. Someone said something about constraints being good, didn't they? And they're phantom types. So phantom types are never instantiated. They don't exist after compile time. But they're very useful during compile time in enforcing constraints. So this is what we can do. If we create a value, say hi, same as before, it's got this type en with fr with de. Now we can get the value, the English value, we can get hello from this by applying the type, not a value, a type, to this say hi value here. This will give us hello. We can say hi de. This will give us guten Tag. If we try and get Spanish, this will fail, but it fails at compile time. Now this is the key difference between a typed map, which is what this is, and a plain map. The plain map doesn't encode the values that are stored within it in the type. It doesn't know. You're at the mercy of exceptions if you try and call them. Whereas we've been careful to make sure that our iString, part of that type is what you can get from it. And we use that information. It's very useful. And it means that if we've got a say hi, if we've got an iString called say hi with this type, we can guarantee that we can get an en from it, a de from it, an fr from it. There's no risk. By construction, it will work. So the iString is like I said, a typed map. This type T here would be the intersection. So, for example, we can create this has nothing to do with the map in the standard library, by the way. I should probably have called it a different name. Map of int with string. Look, int with string. There is no such thing as an int with string. This is just to emphasize the point. But we can have this as a type. We can get an int from it. That's fine. Compiles. We can try and get a symbol, but this won't compile. You can't do it, and that's because we have this constraint here. The type you provide, v, must be a supertype of the t type. So int is a supertype of int with string. String is a supertype of int with string, but symbol is not. That's how we can add this constraint and have it work, and be confident that if it's compiled, it will be guaranteed to run. So, why the big deal? Well, I think I've just explained that, haven't I? If we, it will definitely have those types that are in the intersection there. Accesses are checked at compile time. They're guaranteed to be safe. So you might have thought, me talking about modes earlier, this would be a use case for modes because we're trying to get a value from a map which might fail. It won't fail. We don't need modes here. However, this only works if you know at compile time the exact types you're getting out. What if you have a string which comes from user input? It might be en, it might be fr, it might be qz, which isn't a language. How do we know that we can, if that value has been provided, how do we know that we can then later get that value from our iString? We've got no guarantee. We have no type. That's the reason. We have no type representing that we can check. It'll be an abstract type. It's unknown. And for example, with qz, what if it doesn't exist? So this is how we get around it. We have a thing called locale. Now we parse a string. So we've used fr here. We create we create an object from which we can parse a language string, whose return type, once parsed, whose return type will encode the possible languages that can be. So the parser that we have here, it will check this lang. If the lang is en, then it will return a locale. The return type will always be en with fr because we don't know any more than that at compile time, but we do know that if it succeeded, it will be locale of en with fr. It'll work with fr as well. If this happens to be de, this parser will fail. So here's the example. We then apply as a value to our I string the locale, the parsed language, which is either a successful language or some sort of failure, and this will then give us hopefully give us the string back. We've been here before. There is still a point of failure. That parse method can fail. So this is once we've constructed a locale, once we've successfully got a locale of en with fr, we know that will then as long as the en with fr is a supertype of the type of the map. So en with fr is a supertype of en with fr with de. Think about it carefully. Yeah. We can successfully get that from the map, not the other way around. And that is then a safe operation, but the parse method can still fail. We've eliminated every point of failure apart from this one where we parse the string representing the language. And that necessarily must exist. If we're accepting arbitrary input into our program, then we do need to have a point where failure can exist. And this is where we can use modes. So we can have this parse method take an implicit mode and return an appropriate response based on the mode that's in context. Is everyone okay so far?
Yes.
Good. There's a question.
No, just saying yes.
Oh, sorry.
John?
Yeah.
Can you go back to the previous slide?
Yeah.
Sorry, because you started with fr there. Why not with en? The lang? Or both or something like that?
I started with so this is actually known at compile time in theory. Yeah, we could in theory have this this value known. Imagine this was sort of console.read, and you type in the value which isn't known at compile time.
Yeah, but I see some asymmetry there in the sense that it might as well have been en.
Well, exactly. Yeah. So this is in my example. It looks fixed. What my example should demonstrate is that this is not known at compile time. So it could be console read.
Okay, I see.
Yeah.
Okay.
So using modes. Rhetorical question for now. Could we use modes in our command line API?
Sure.
So conflicting possibilities. Okay. Right, what have we done here? Okay, so we've defined a size parameter, same as we had with our best so far command line API. An integer parameter, which is the size. We parse, or we sort of semi-parse our string arguments, and we import return option, and we get the size param from our parsed command line arguments, and because we've got return option, we get sum of 10 back rather than just 10 or an exception thrown. What if we had this? What if we had we introduced a new command called Resize, which there are two ways of using this hypothetical program. Either we have an area parameter, or we have a width and a height. It won't work if we only provide a width. Won't work if we only provide a height. Let's say it probably won't work if we provide an area and a height. These are the two ways you would want to invoke this. Now I had a go at trying to write some code to handle that, and it's quite long. There may be mistakes in here. but we've got we're using option as a monad here, and we're flat mapping, and this is just not that easy to read. Agreed? So in this example, there are three separate places failure could happen: when reading the area parameter, when reading the width parameter, or when reading the height parameter. Could we reduce this to a single point of failure? That's the question. Now this is kind of how we would like to describe our the requirements of that parameter. Either you have an area parameter, or you have width param and height param, and the parentheses by precedence go around the width and height. So let's do that. Let's just make that our syntax. Now this will create us a parser in the same way that we were able to say en pipe fr.parse. We define this more complicated thing with pipe and we can parse string arguments, and that may succeed or it may fail. Let's assume parse is using modes still, so it can still fail. We do have to handle failure, but we're handling it in this one place. Now I don't know what this slide's about. So this is the simplest example you can have, including both union and intersection, or pipe and ampersand. But think of a command like git. So many different parameters are relevant at different times that could be hugely complex. You've got nested disjunctions and conjunctions. It's a very complex thing, but written in that sort of syntax, it would be probably as concise as you could reasonably make it. So this is what we're doing. We're going to represent parameter A and parameter B and parameter C, so a conjunction, as product of this intersection type, the types of each of these things. I should probably have written this product A.type with B.type with C.type. That's a mistake. This is value level code. This is type level code. Likewise, the disjunction, we represent that A pipe B pipe C, which is a coproduct. Is everyone familiar with products and coproducts? Coproducts are of these possible things there is exactly one. Products are of these possible things we have exactly all of them, and they are duals of each other. We need to define, in order to get this code to work, to compile, we need to define combinators, pipe and ampersand. Now this is pseudocode. It's meant to look like Scala, but this is how we would want to interpret a pipe operator. Now I've got this wrong. That pipe should be an ampersand. So maybe if I highlight it, it'll look more like an ampersand than anything else. So in order to work out the return type of something given given a left-hand side and a right-hand side of that combinator, we kind of want to pattern match on what those types are. So if the left-hand side is product of something and the right-hand side is product of something, then the return type will be the product of the first something with the second something. So if you look at all of the possible cases, the right-hand side is always product of x with y, but where the y comes from and where the x comes from are different. Now they have to be this way round. It has to do this one first because this is most specific. X and y are arbitrary. We don't know what they are, but with product, that is a very specific type. So we match on this first. If this fails, we then try if just the left-hand side is a product but the right-hand side is something arbitrary, then the symmetrical version of that. And then failing that, they're two non-product types. So we just return, or the return type will be product of x with y. So again, I'm thinking on the type level. I'm thinking how I'm going to return, or what return type is going to result from the application of this this combinator. This is basically the same, except this should be a pipe. These two slides are joules of each other. Can everyone read this? Can anyone read this? Yes. Okay. What we're going to use is we're going to take advantage of a feature. Is feature the right word?
Side effect.
A fact about implicit resolution, which is that if an implicit that is imported, is inherited from a parent type, has lower priority for resolution than one in that actual in the type it's inherited into. So this isn't implicit yet. I've just used the code, the pseudo code from the previous slide. This this one at the bottom has higher priority than these two, which have higher priority than this one. So they've actually no, they're in the same order because I've put the traits this way around. So this is what we want. We want in the case where we have a product on the left and a product on the right, we want to combine them into a product of the parameters of those. And failing that, failing the next one, we fall back to just create a product of the left and right types. So this might not make complete sense because it's well, firstly because it was written very quickly last night, but also because it's a combination of pseudocode and kind of actual code. This is the translation of that pseudocode into actual code, excluding the implementations. So why have I created these implicits? Well, I need if I'm applying if I've got a combinator, the pipe or the ampersand, I need to combine the left and right in such a way that I return a new value of a particular type. And to work out the type, I'm going to use implicits. That's one use of implicits. We're using we're using the refined type of these implicits to work out what the return type from the combinator will be. So this is quite complicated. I'll repeat it. Possibly better than I said it the first time. Possibly worse. We're going to take advantage of resolving implicits with the best specificity we can to work out what the return type from our combinator will be. So if we have a product, so if we go searching for a comb and the types we search for match this type here, product of x and product of y, this is the most specific version, then this imp4 will be resolved. That will be how implicit search finds a parameter to match that type. But the compiler knows a little bit more about the type. It knows exactly what the inner type return will be. So this is where we put the resultant type, this product of x with y. Does anyone understand this? Yes. There's more yeses than I expected, actually. Failing that, we will resolve one of these two implicits. Failing that, we go to the most general version. So this will always resolve if we're looking for a comb of two things. This may be the most specific thing that resolves, but this is what we get. And by virtue of grabbing that implicit, by virtue of the refined type here, return equals product of x with y, we're using the compiler to derive the return type from our method. So this is what we can do. We can again define area param with width param and height param. Sorry, area param or width param and height param, and we can parse some array of strings. And the type we get back from that will look like this. This is the type that will be created by virtue of that one line parse action. Coproduct of area param.type with product of width param. This is a line break. Width param.type with height param.type. So this is the type that various implicit applications have caused to be created, which will be the return type of our two combinators that have been applied. Now, what can we do with that? Is there a question?
Yeah, I've got a question. Isn't that with magic somewhat fragile? Isn't int with int and int, and so we've got a co-product or product of one int instead of int with int?
Yeah, so it's a good question. The question was, is the type fragile? So is int with int the same as int? And I think the answer is sometimes, but I think it also doesn't matter too much.
But shouldn't compiler optimize it in some future versions?
So it might be normalized. Int with int might be normalized in some cases to plain int, but does that matter?
Maybe.
So I don't think there are any cases here where it does matter. So what int with int or int with int with int with int is saying that there is an int.
Or we have 5 ints, if that's a product of int with int with int.
Not sure I follow, but I don't think it's a problem in this particular instance. Yeah, another question.
Just to check about the precedence, is it not going to be resolved as first the co-product of area param and width param, which is then a product with height param?
No, I think ampersand has higher precedence than pipe.
Okay.
That's correct, isn't it?
Yes.
Yeah. Luke.
In your implementation, so you had the last one of the implicits was with an x and a y, which was then making actually the product. But you have to define the same thing for co-product. So is that not going to have? Don't you need two comps or something, because there will be a conflict if you with the same implicit for co-products?
So we would have all of these implicits as well for equivalent versions for co-products.
With the same or another comp?
Sorry?
With the same or another COMB?
Oh, we'd give it a different name.
Okay.
Yeah, sorry.
Okay.
That's.
Okay.
I wanted something short,
Okay.
but this is for the ampersand combinator.
Okay.
We would have a different type. Yeah, completely different type for pipe. So given that we've parsed this into PS, into a value called PS, the type of this now knows that, assuming this succeeded, that we've either had a valid area param or we've had a width and a height param. If we didn't, then that will fail. So given that is it's a co-product, can we do something with that? Can we safely make use of that co-product, avoiding any possible failures that may result from accessing those values or checking they exist? And we can. So the co-product type that I've provided in the Rapture command line library has a method called handle, and it takes var args. Each one will look like this. The API will say, well, we're going to handle area param, which is one of the alternated options, area param by some function, and we're going to handle the other side of the alternation, width param and height param, by this this lambda here. Now, there are various checks going on here which are important, and let us let us write this code very safely and with some certainty that it will succeed. Now, the handle method, the type that's inferred, or one of the types that's inferred as a result of calling this, must be, I can't remember if it's a supertype or a subtype, but it must be a subtype of PS's type, the alternating type. By the way, this is where the slides ended last night. We want this handle, this call to handle, to be total. We don't want to provide a handler that doesn't deal with certain cases. So we have to handle area param, and we have to handle the other alternative, which is width param and height param. So those are the two things we have to include in our handle. These are the two alternatives, two cases, if you like. But I haven't used case because case allows us to write inexhaustive matches, and this doesn't bode well if you forget one. We want the compiler to tell us you've forgotten something. You've forgotten to handle area param by this handle method. So the way Scala works with varargs is to look at the type of each of them and find the lub of those. Now, the types here are reasonably complex, but I've arranged them in such a way that the lub, or part of the lub, will be the intersection of area param and product of width param and height param, or width param with height param. So the intersection will match, and must in fact match, in order for the handle method to be applied, must match the type of PS. If it doesn't, we'll be told that it's not exhaustive, or we will be told it's a compile error. The return type from this handle method is going to be the lub of the return types of these lambdas. Now, P of area param, this will always succeed because the type of P, the type of this parameter, is this right-hand side here. Sorry, it's this left-hand side here. Area param, does area param have an area param in it? Well, yes, it is. That is what it is. So this will be guaranteed to succeed. And the type that gets inferred for P, the P in this lambda here, ensures that. Likewise, different P, different type inferred. The type of this one will be a product of width param type with height param type. The lub of the return type here, right? So the inferred type P means that we can definitely get width param from it. We can definitely get height param. We couldn't get P of area param on here because from this type here, we have no guarantee that area is on this on this particular version. Now both of these return ints. Area param was set up to be an int, width param was an int, height param was an int. These both return ints, so therefore the return type of handle is itself an int. But it's guaranteed to be an int. There is no chance of failure. This is what we've set out to achieve. Even though I explained it probably quite badly, and most people are scratching their heads at the moment as to how this actually works or what it does, but we've got a total function that is guaranteed to handle all of the possibilities, using the type system to enforce them. And I don't think we can do that. We can't do that with cases, and there is no risk of any failure happening in this code here. All the failure happens early on in one place in the parse method. If that fails, then we handle it up front and worry and we don't have to worry later about accessing values that might not be there, or forgetting to handle alternatives. Nobody understood that, did they? So in summary, having multiple places where our code can fail is not useful. We want to minimize what I've called the surface area of failure to as small a point as we possibly can. Put all the failures together up front. I mean, we don't really care if we fail to parse the parameters with I mean, there might be multiple reasons why parameters fail to parse. We don't really mind which one it's failed. We maybe grab hold of an exception which gives us more detail on what's not worked, but basically by concentrating, by focusing those failures into a single point, we've reduced the amount of code that is subject to bugs. And we've done this by encoding facts about the structure of the type in the type itself. Structure of the value in its type. And consequently, the compiler will enforce many more constraints on, can easily enforce constraints on accesses, on operations on those values, such that we don't have to be concerned with exception handling or anything that might deviate from a happy programming experience. And ultimately, we've reduced the surface of failure. So that's the main idea I'm trying to get across today. There's one other interesting thing we might be able to do, and I'm not sure. I haven't tried it, and I'd be interested if people have any thoughts on it. Whether we can use this to improve performance. Now, if we cared about performance more than type safety or ease of use, then basically we'd just put all these values in an array, and we'd be very careful to write code that just indexes arrays in the right place to make sure that. We'd be careful to make sure that it doesn't crash, but I mean, there's no compiler help there. But it would be basically as fast as it could be, and indexing into an array is pretty quick. There's no hash codes need to be calculated, no equality checks, and so on. So accessing value from our map would potentially be as fast as that if we could actually use an array to back to back our state, rather than the various hash maps that we're naturally using. So I've said all that. So, but is it possible to use an array without actually having the reasonably horrible interface of an array? Well, I think it might be. So given an access to our map, our types map, we know the type of the key we're looking up, we know the type of the map, and we know both these things in advance of actually running them. So let's look at that type intersection. We can order those types. Let's just arbitrarily say we'll put them into alphabetical order, just because we need to come up with some order. So alphabetical order of the name of the type. Now, in each, this gives us one slot for each type. We then have an array that backs that intersection of types. Each index of the array representing that particular value for the for the type in the intersection, and we re-implement it using a macro. So I'm a little disappointed that having gone this far with just the type system, we're falling back on a macro to do this cool stuff, but there's no way around it, I don't think. And if we're accessing, for example, int in something that's int with string with symbol, well, int is, if we sort them in alphabetical order, int with string with symbol, well, they're already alphabetical order, so it would be the 0th element, and the macro will translate that, in theory, to an access on an array of the index 0. The macro has all the information it needs to do that. The risk, as someone alluded to not long ago, is that type is not quite stable. If we have int with string with symbol, that's kind of the same type as int with string with symbol. Will that cause problems? I think this is where we could do some experimentation and see whether we could get much faster, much safer, much more pleasant to use structures, not just for command line arguments, not just for languages or anything like that, more generally. So this is all in Rapture CLI. This all works, apart from the performance stuff. I haven't got time to give you a demo, but we're quite a long way over time. It's work in progress. It doesn't have much finesse, but fundamentally all these things I've described work. The compiler doesn't crash too frequently. And I think there's a lot of potential in this. I think with a bit more work and a bit more effort, we can have something that's genuinely very useful at reducing the amount of error handling we have to do. One nice thing we can get from this is that by defining an expression for a complete command line, we can kind of reverse engineer a tab completion for that. Now, I've done this with an earlier version of Rapture CLI. I need to port that over to the new dependently typed Rapture CLI, and you can basically define your command, what it does, get the parse it, and in the process of parsing it, automatically generate a tab completion list that your shell can use to determine what happens if you press tab. So anyone who's written a sort of polished command line application and had to work on either bash or ZSH tab completions suddenly gets that for free. And this is something I've used a couple of times already. But I would like help. I only have so much time. It's evident by how many projects I have left unfinished. So if anyone thinks this is interesting or thinks there's potential here, I would love for you to become involved with Rapture to take these ideas further, to pad out the APIs that I've got at the moment, and have something that people can use. I mean, most of you put your hands up when I asked if you had developed command line applications at any one time. This could make that development process a lot more pleasant. So talk to me. I would love to hear from you, and hopefully we can make software more safe and less error prone. That's it. Thank you.